Okay, great. Thank you so much for the introduction. Thank you for having me. Thanks everyone for joining this amazing conference. I'm very thankful and very inspired about the community and all the things that we can achieve together if we pull in the same direction of combining robotics, climate science, and sustainability science. Now, I'm working on sustainability robotics, and I'll give you a bit of an overview of some examples of how that looks like, what that means. Now, I started the lab at Imperial College in London in 2012, and the second PhD student was Thomas Creedy, actually, who you see here in this picture. And the project was creating robots that would place sensors in the rainforest here in Honduras, and then measuring biodiversity. Now, at that time, really, the community, like the technology was not ready yet. So we didn't have many robots that can do that. And so using those type of tools that were available at the time were not suitable for these complex changing environments. Since then, we have developed partnerships with the Empa Material Science and Technology Institute in Switzerland, Empa, as well as now with the new shared faculty position with EPFL, where we have the Laboratory of Sustainability Robotics. So the idea is that we have robotic tools or platforms, or like the Swiss Army knife of environmental sensing, which then can collect data, can also influence the environment and repair the cities and the infrastructures. So all of this towards the vision of creating a sustainability robotics as a shared theme, shared research discipline between environments, robotics, and material science. Now, if you think about nature, and I think we can learn a lot from them, we see that they co-evolve aerodynamic sensing, control, navigation, actuation, and all of this into a platform which is very capable to deal with the uncertainty of the environment. And this is something that I would like to emphasize here, which is that we can build on both the control sensing planning-based methods in nature, but also in robotics, where a lot of computing is needed, a lot of sensors are needed. But also equally, we can benefit from the idea that the physicality of the robot or of the animal can help in the intelligence. So this is something called mechanical intelligence, as you see on the left side with antennas or the legs of flies, which really help them to attach to the surface. So it's material science, it is the morphology that does the computation. So the mechanical intelligence is equally important as the computational intelligence. So if you're able to combine the two, then I think we have a winning recipe for creating lifelike robots. Now, sustainability robotics in our lab consists of different themes, from extreme environments to infrastructure sensing, to forest sensing and biodegradable robots, and even to robots that can collect data in aquatic environments or to repair tasks. I'll show you a couple of examples of how this can look like, and just to get a flavor. I will not give a lot of detail given the short time, but just give an overview. So the first one is on forest sensing, and there we have developed different methods of how to do that. An example here is to use the WSL dataset of tree density, like leaf density mapping. And then we use that to train a YOLO algorithm, which we then complement with a synthetic dataset, so a game engine-based dataset, to then learn the feature extraction. Like this, have a robot that can fly through the environment, collect videos, and then map the leaf density of different trees in real time and relatively in an absolute sense, to then collect this data and give insights onto the health of these trees, assessing the crown loss, which happens in ash trees. So the ash dieback is a big problem. And so visual methods can already help in doing that. But then these robots, of course, need to be autonomously flying through the forest. And there is something we can use called the optic flow divergence, which allows us to estimate the distance to an object. And this by looking at the expansion field on the retina. So by doing that, we can have an estimate on the environment. And so the closer we get, the bigger the expansion is. And this expansion then can be used as a proxy to the distance to the object. But this only works when the object is flat. Now, because of that, we now included something that we call the fictitious wall hypothesis, where we have a system model using observations not only on the optic flow divergence, but also from the accelerometer and other sensors, to then have an estimate on where the actual surface is. By doing that, we can implement on very small vehicles, like you see here, the capability to fly in the forest, stop in front of objects, and enter through openings and narrow environments fully autonomously. And this using only about 20 grams of electronics and battery. So this is much less than an autonomous car or it's like an autonomous robot typically would use, having computation and sensing on board. So here it's a minimalist sensing that can be used to then fly through those environments. We can then combine this even with tactile sensors, as you see here, enabling the robot to engage with the physical environment, and like this have the antennas and the physical engagement, and on very small platforms of less than 100 grams that you see here. Okay, we can also then look at impact resilience. So here's a project where we looked into origami-based structures around the robot that can crash into the object, and like this remove the peak force and decouple the yawing moment on the platform. We can parameterize that, manufacture this, and then test it compared to on the left side here with a normal robot that has a protective cage. And this kind of rotorigami or origami-based protectors can really be more resilient, more versatile, and like this enable the robot to move through complex environment, even with small crashes. So a combination of minimalist sensing in combination with resilience to impact, I think, can be a way how to improve the autonomy of small objects small robots in complex environments. Now, can we even look at using the interaction as a way to have functionality? And for this here, we looked into metamorphic full body perching of robots that can fly and then perch to the surface by doing metamorphosis, using different carbon fiber, polyamide, latex composites, allows the robot to fly and then perch itself to the environment. So as you see here, so it flies and then hugs the tree, like a tree hugging robot, really liking the nature so much that it naturally wants to do that. And then being aloft, being suspended or perched, it can observe the environment, collect acoustic data, maybe take even samples from the tree and so on. Like this being a very minimally invasive manner of doing that, right? The flight is not, the flight can often disturb the animals in the environment, but if the robot is perched, then I think it can actually be less invasive. Okay, so another method, if you cannot approach the surface, is to shoot sensors directly from the platform. So here's a system that can do that by detecting the tree trunk and then shooting small sensor pods with a precision of a few centimeters on a few meter distance, as you see here. So like this, it places the sensor very precisely and effectively. Like this can then collect environmental data. So one example of what to collect is shown here. So it's a test in Croatia in the forest, where we wanted to collect biodiversity data across the canopy, so across the height of the tree. And so here it shot this dart. And the dart then has acoustic sensors on it. So this then collects the acoustic signature of the environment, which can be analyzed using machine learning tools to identify the abundance and richness of species in those environments across the canopy layers. This means it quantifies which birds are there, how many of which birds based on the bird sounds and the machine learning algorithm that does that, to then kind of have quantified data of those of the biodiversity in those environments. Now here again, it's better to do that than to climb up the trees potentially, right? It's because it's less invasive, takes less time, is less risky, and is less costly. So having robots can be a useful tool to really obtain this quantified data. Now, a question, of course, here is what happens to the sensor afterward? And we had a mechanism to remove them again with the robot or manually. But really the key question is how we could build those sensors that are deployed from the robot to also be minimally invasive in their material, in their environmental impact. So can they be deployed? And then as they are deployed, can they biodegrade in the environment? Now, this is something that we call transient robotics, or benefiting from biodegradable materials, electronics, and so on, to enable the sensors to be deployed and then collect environmental data, maybe even tag animals, and then use this data for insights on the environment while leaving zero environmental footprint with the robot itself. So this transient robotics, I think, is a new field that really combines structural design and materials, actuation design and materials, and as well as sensors that when coming together really is what the core of the robot is made of. So in terms of the structures, and I'll move quickly through that, we have a number of publications on this, but just to give you a bit of a highlight here. On the structures, we work on cellulose composite cryogels, which are basically cellulose mixes with gelatin or starch that then can create those porous structures, allowing the robot, allowing the structure to have certain performance that when built and have certain performance of biodegradation, as you see on the top right, when it needs to biodegrade. So we want to time the structural performance in terms of structural strength and structural biodegradability as we go along. So this is aligned with the mission profile of the robot. The sensors are screen printed or inkjet printed carbon inks on the surface of the cellulose material, allowing us to build those kind of sensing structures that is on the right, where we have the ailerons that are being sensed in deflection based on resistively changing kind of materials on the surface of the robot. And all this is fully biodegradable. Equally, the actuation can be humidity actuated structures, as you see, for example, in those gliders that we built in the previous slide, but also in those helical twisting actuators, which have moisture responsive layers, carbon conductive layers, and cellulose substrates. And then by heating them, we can create those kind of grippers that would allow the robot to attach, the sensor to attach itself to the environment using this kind of humidity actuated actuators, as you see here. So there's a few highlights. I'll move quite quickly just for time reasons, but I think the idea is to use cellulose materials, which are a form of biopolymers that are very abundant and very neutral in terms of the footprint, and use that in various ways for sensing, actuation, and structural design. So the vision overall for this is to really build the robot, then use the robot, biodegrade it, so it biodegrades naturally or dies, and then even can potentially regrow. So can we use biohybrid systems that would allow the robot to move then again, have life again, and be used again. So transient robots and the circular economy of that is the key. Good. So then I have a second section here, which is about infrastructure monitoring using perching robots. For example, using Spider-Man inspired robots that, for example, you see here building webs in the forest collectively. So here are silk materials that are used for weaving structures in the made up forest here, but by using the compliance of the structures, it can be used to really make support scaffolds in the environment, which can then be used for perching and physical interaction with the environment. So it can perch like this, and then sense the environment being suspended, then fly off again. Okay, so I'll skip through the couple of slides here on this, but I think this is quite interesting and powerful in terms of the method of physical engagement by using tensile elements, which are used a lot in nature. Good. Another example that I would like to share with you is this idea to use robots that would fly in very hot environments. So when I was living in London, I saw the Grenfell Tower fire. And if you remember, in 2017, this killed more than 72 people. So it was really a catastrophe in London that happened because of these facades that were burning. And at the time, we didn't have robots that can fly inside of this fire. And I got a phone call, actually, asking us whether we have some robot that can look for survivors or look at the structural environment inside of the tower. And we didn't have that. But we started the collaboration with Empa, and an outcome of that was this temperature agnostic drone, which uses aerogel materials. Aerogel is a very heat resilient material, for the structure of the robot in combination with the cooling system and the new arrangement of the motors and new structural design to create robots that can really fly inside of very hot environments. So for example, this one here can fly, and we tested it with firefighters. It can fly in very hot environments, being more resilient to this extreme temperature compared to traditional robots. And we did test one, and it wasn't very happy inside of the fire. So this really is more resilient than these kind of commercial systems. Okay, so another example that I would like to share is the question, or is the idea to have robots that would don't just inspect or collect data, but that would collectively 3D print or manufacture the environment. For example, you see this here, where you have robots that would fly, then deposit materials from flight, and like this collectively collaborate with each other, with with humans on the ground and so on to create structures from flight. We analyzed nature, and we wrote a review paper here in 2019, analyzing how some natural systems build and what the principles are of how they build. And so there's some key principles that we were able to translate into the robot. Building, for example, this system here, which can fly, then stabilize the extrusion head, and then 3D print layers in the environment. Now, this uses a particular type of high-performance cement, which needs to harden fast enough, but be extrudable, still soft enough to be extruded, and like this, allowing us to make layers of this material. So it's really like a flying 3D printing head, where it's not limited by the envelope of a ground-based printer, but it's completely open, and like this can build unlimited height in principle. We then also use a scanner, so a scan drone in the loop, because some materials like the polyurethane foam here is unpredictable. So we can print and then have a scan drone in the loop that scans the structure and then identifies how to print the next layer on top of that. So you see that here, so you can then scan, adjust the next trajectory, and 3D print the next layer. So I'll accelerate a bit. And like this is able to build a layer here, a tower of 2 meters height. Really showing that it's a scalable approach, even if the material itself is not very precise. Now this work came out now 2-3 years ago, which was quite exciting because it combines material science with robotic science, with also architecture of what now we can build with that. And so we went to the Architectural Biennale in Venice in 23, showing how now architecture could be transformed with that. You know, this is a new tool in terms of construction.
Professor Kovac, we're going to have to wrap up in a minute or so.
Okay, good. So, okay, great. Thank you. I'll just take a minute to close. 1 second. So let me just I think there was a misunderstanding on duration. Last more information was 30 minutes, but I understand it's maybe some confusion. So I'll just wrap up with two slides, if that's okay. So the key thing that I wanted to emphasize on how we can build that. So there are a couple of examples. So we also work on others like aquatic systems that can take water samples and so on. But what I think is important is the philosophy of how to build those types of robots. And to do that, we call this the physical AI as a method of development of those types of robots. And the key, I think, here is to really co-evolve the materials and the questioning materials, the robotics, as well as the environmental science questions. And if you co-evolve this together, I think we can create those lifelike robots. Also, I think the bio-inspiration is important, and I think so in 2014, I wrote a paper on that, on how we can take this bio-inspiration to create those types of robots. So I think this philosophical foundation, I think, is quite relevant for making those robots, as are the test beds where we can test them. So in Switzerland here, we built a new robot test bed called a drone hub, which is this cage structure where we have various environments where we can really test the new generation of those sustainability robotics. And this is open for collaboration. So with this, I'm happy to wrap up, give you a bit of a summary on the sustainability robotics and autonomous drones can be used to quantify biodiversity. Then we can see that bio-inspired methods can really increase capability and robustness. Metamorphosis and changing of morphologies can help in doing that and brings us closer to those lifelike robots. And physical AI is this method of how to evolve that. Different test beds, I think, are important too. The drone hub is one of them. And I think if we team up together, then really we can make a difference altogether. So thank you very much.